Then after this struggle, we'll go to the recurrence formula for associated Legendre function, or I mean, start with the associated Legendre polynomial, but I again won't go through it because it's a long derivation. That's really long, and I actually make quite a number of video to explain to derive all these recurrence formula. So I just outline how you get it, because we have done this this kind of derivation before, like the Bessel function and the Legendre polynomial. Basically start with a generating function and take the derivative of that with respect to two arguments, and you get two recurrence formula. Except that now for this PLM, you have two indices, so you have actually one more independent recurrence formula, or totally three independent recurrence formula. But again, for convenience, you combining all these and we derive a bunch of other formula that might be easier to use in one way or the other. But then you start with actually start with the associated Legendre function related to the Legendre polynomial. Basically start with this. This is equation 15.78. So you have this given by minus 1m dx and okay, we start with that and then go back to the generating function of our piece of L, which is the 15.6 g xt. This 1 over square root of 1 minus 2 xt plus d square equals this sum over, now here, change to L in as your summation index. This piece of L to the power L. Okay. So now the idea is to get the generating function for this one, for the associated Legendre polynomial. You basically take m derivative here, or including this. So basically, you apply this operator on both sides. So apply the operator and on this g now is equals to, because this operates only on x, doesn't affect t. Supposedly, this becomes this when you apply, becomes this PLM. Right. And you can do it this way, which require you to take the repeated derivative over this g function. This is over x, and that is fine. That is you could do that, although it's tedious for arbitrary m, and then final formula maybe. I mean, that's maybe more complicated. Another trick to do that is I showed that in my video. So you do it one at a time and show that in order to every time you keep the L, you actually increase this L by one order, right? And then so finally, if you do it that way, it's just like a little trick. But if you do it that way, then finally, this kind of operation will give you the generating function for this guy, for this associated Legendre polynomial. Is basically instead of consider this thing, you consider this generating function for the index m, which is this minus 1 to the m power, which is coming from this factor, m minus 1, double factorial. And then the same kind of factor here, it's t plus t squared, but to the power m terms, 1/2. It's complicated, but then that would be equals to sum over s. Your textbook using this summation index s, but then the p is instead plm become s plus m, and then m x to the s power. Right, and now the only difference is that instead of L, you could write it S plus M. So you sum over S from 0 to infinity here, and then you're not starting from 0, not starting from PS. You start from PS plus M. So it's a little different from what we try to do. This start with P0M, right? So, but you start with S plus M, and that's due to the trick that I mentioned. This every time you take a derivative, you actually shift it's easier. The left-hand side becomes easier if you shift this the lower index, the subscript by 1. Every time you take the derivative, you increase it by 1, and the summation will still start from 0. This S index will still start from 0, and you keep doing the m terms, then you get to this this function, and the right hand side is summation of this associated Legendre polynomial in this form, Sm, and then you can use this form to do the usual trick. Take the x derivative, take the t derivative, then you get two recurrence formula for this p, like this script p, and actually the one more other than the two derivative, one more recurrence formula is obtained by the other trick. In this case, this trick is multiply the same factor to this m, so multiply by 1. This is equation 15.85. If you multiply this factor, you can see m, but you multiply by g sub m plus 1, right? If you have a g, you shift this m to m plus 1, so this becomes m plus 1. So there's an extra factor here in the denominator, but you multiply by the same factor, basically cancel this extra factor, right? And other than this m for this one is all shift to m plus 1. This shift to m plus 1, right? And then you convince yourself that what the extra is, because this shift to m plus 1, you get an extra minus sign. This shift to m plus 1, because it's double factorial, you get 2m plus 1, right? And the rest is just the same thing. Okay, so this is another way to derive another recurrence formula, because if you substitute this one to here, so this one involve all this object with m plus 1. This changes m plus 1, this changes m plus 1, right? And then now you have these two terms that involve another extra t factor and extra t square factor. So all this will shift this s, right? Because you multiply another t, you need to shift back. So you change the subscript again, right? So and then compare with the original one, and you get another recurrence formula. That using this method, what you derive is the equation below 15.85. That basically all these, you have three terms in here, involve m plus 1 in the superscript, and then they involve different subscript because of the shift, because of this multiplied by t, this multiplied by t, and then one term you multiply by x. So, and then the right-hand side is just this factor multiplied by the original one, this one. Right. So if you write it down explicitly to explain the method, so all these trees are involving m plus 1. So basically this one. And then the shift will give you 3 of them. I mean, the first one you don't need to shift, so it's this s plus m plus 1 because this is for t m plus 1, so this change m plus 1. And then you have the one that involves 2x factor. And then because of the shift, you have the s plus m, still m plus 1. And then finally, this one, because of square, you change this to s plus m minus 1. Still m plus 1. So, and the right-hand side is just this one. Okay, so that's the equation 15.84, the equation below 15.85. So this recurrence formula involves changing the m, the superscript shift by 1, and then the subscript is involving plus 1 and minus 1. So that's an extra recurrence formula other than the 2 recurrence formula coming from taking a t derivative of this one on both sides, and then taking an x derivative on both sides. And the x derivative will get the recurrence formula involve the derivative of the associated Legendre polynomial. The other taking a t derivative is just shifting. It's just shifting the subscript, right? So with the actual deriving that, you can just write out. So the first one, taking this t derivative involving shifting just the lower index of the subscript. So that will give you equation 15.83. So yeah, you just notice that they all have the superscript m because you don't shift the superscript. And then yep, 3 terms. That's x here. And then s plus m. Right. So this is coming from the taking the t derivative of that, and you finally you show that this equals that, and that is fine. And when you take the t derivative, everything still be the same index m. The superscript doesn't change. So this recurrent formula, just like the original recurrence formula for the Legendre polynomial, you just shift the lower part, which we call L. So but all these two involving this s plus m. But if you like, you can now do a change of variable. Every time you see s plus m, you just call it L. The change of variable. So basically, s becomes L minus m. So, but for this one, you just easy. Just shift all this to L. This L plus 1, this L minus 1, this L. So that would be equation 15.86. But this one, you change this to L. But then whenever you see s becomes L minus m. L minus m here, L minus m. And then you get 15.84. So that's another trick. So using that, you get all this subscript involving s, but then you make change of variable, go back to L. So and that may be more familiar, more a little easier to use, right? So that's two that are involving just the function or just the polynomial without the derivative, because you're not taking the derivative with respect to x now for both of them. So, but they are independent, and you can see that because this one doesn't involve changing the superscript, and this one involves changing the superscript and the subscript together. And sometimes it's easier to derive another one that involves just shifting the superscript and keep the subscript the same. I think one of these things would be like that. I haven't talked about that, but the next step would be going back to associative Legendre function. Say, like, you look at 15.87, after some manipulation, you can get a recurrence formula that involves the same L. So the same L, but different M. So that's 15.87. But that is coming from all these two, and then the definition of the Legendre polynomial, Legendre function, associative Legendre function, which is given by which? Yeah, 15.74. So ALM is defined as 1 minus x squared m divided by 2 multiplied by this associative Legendre polynomial. Right. So this is you can convert all this to PLM by just whatever you see this script P, you just multiply by, you just become PLM divided by this factor. So whatever the appropriate factor, whatever this M is, you divide it by the appropriate factor to the left-hand side. So every one of them, if they have the same M, then doesn't matter, because they all have the same M, so you divide it by the same factor, it's just cancel out. So this one, you automatically just change it back to this script P becomes the original P, right? So it just becomes a associative Legendre function, the same recurrence formula for script P and non-script P, right? But not this one. So whenever this, because this involves m plus 1, so you have this, you need to divide the m plus 1 divided by 2 to convert to this capital P, right? But this one's m, so it's divided by the other factor, 1 minus x squared to m over 2. So that means the recurrence formula using this one involving this original associative Legendre function will have this extra 1 minus x squared factor out. And I think this one is, this one looks like, because they have 4 terms, this one looks like one of these equations in 15.89 and 90. Right. So that you see that they have this 1 minus x squared factor, right? So other than that, they are basically the same. So you just need to convert the two functions between the two functions. And now the final one is taking the x derivative. That will give you the pi involving the derivative. So the p pi, either the script p pi or the derivative of this one. I think I'm out of time, but then to the recurrence formula that involves the derivative is 15.91 and 92. There are two forms because you can use the other recurrence formula to shift from one to the other. It's just depends on your application. One of them will be easier to use than the other. And so finally, the recurrence formula, the list of recurrence formula for this form listed in your textbook, list 87 to 92. the 3 of them are independent, and the rest are dependent. And then obviously you can keep deriving different recurrence formula, just combining all these and derive other formulas that may be easier to use. So and the application of the recurrence formula is just at least one of them. You can just based on for example, when your m equals 0, m equals 0, you just get back to the Legendre polynomial, and you know that you can construct all the Legendre polynomial using p equals 0 and p equals 1. And once you have that, you use the formula to shift n to start from m equals 0. You can shift to other m numbers. Say you have 0, then you can shift it to m equals 1, and so on. And so finally, you actually can construct all the PLM with just P0 and P1. After you this, and then you can construct all of them, and that's one way to do it. Another way application is to calculate the derivative using the derivative recurrence formula, just like what we did before. I think that that's pretty much it.